All right. So on the next page, we have a couple of rules, new rules. They're not really new. They just seem like they're new. Basically a recurrent theme in the course. Like, oh, no, it's just a carryover of a previous rule that you already know. So if I were to tell you that cosine of 2x is equal to, I'll just choose one of the three variations of the double angle rule for cosine, 2 cosine squared x minus 1. I could solve this. It's already solved for cosine 2x, but I can solve it for cosine squared x. If I do that, I add 1 to both sides. So I get cosine 2x plus 1 equals, yeah, that would be 2 cosine squared x. And then divide out the 2, cosine squared x is equal to, I'll just reorganize. You get that equation, right? So it's just an extension of a double angle rule for cosine, which is why throughout the course I've been saying that your double angle rules are things that you want to know, right? Because then this is not anything new for you. Why would this be beneficial? Well, we can take the antiderivative, and I can even simplify this further. Actually, I'll do this on the app. Clean it up a little bit. This is the same as saying 1/2 plus 1/2 cosine 2x. And the same would be true for the sine squared. All right. The benefit of doing it this way is that we don't know the antiderivative of cosine squared x at all. We don't even have a technique for that. There's no integration by parts, nothing like that. But we can very easily find the antiderivative of 1/2 plus 1/2 cosine 2x. Right? So making that substitution takes something that previously we would not have been able to do, and makes it into something that we can easily do. All right, so same idea for the sine. All right. So right off the bat, we're given a definite integral where we have powers of 2 for both cosine and sine. We don't have a power of 3. We don't have a power of 5. We don't have an odd power like we had in the previous two questions. So we don't have the ability to save a factor. Right? We can't just factor out a cosine or a sine to make it more convenient. So we need something else, and that something else is the double angle rules. All right. So substitute. So I have sine squared x. I wanted that to be in red. It's going to be 1/2 minus 1/2 cosine 6x, yeah. All right. Because the model has us relating a sine squared of x to a cosine of 2x. So whatever the argument is in your sine squared, we're going to use double that in the expansion. All right, so we're doubling the 3x, and that would be the same thing for cosine squared, except we're using a plus sign. All right, and that makes life a little bit easier. Because when you distribute, you're going to have a difference of 2 squares, right? So we just have to multiply the first and the last terms. We're going to have 1/4 minus 1/4 cosine squared 6x dx. What's going on here? Can I apply a rule here?
It looks like the first cosine squared.
Yeah, it looks like the first cosine squared x, so we're going to do another substitution here. So 1/4 minus 1/4 times what? cosine 12x, yeah, so plus 1/2 cosine 12x dx. All right, so it's got a little bit of oomph to it, but nothing too crazy, nothing you can't handle. Distribute the negative 1/4, so it becomes negative 1/8 minus 1/8 cosine 12x dx. We have some like terms that can be combined. We'll take care of that. What's a quarter minus an eighth? An eighth. All right, so then we could just integrate, and then we'll be done. The 1/8 is going to become x over 8, or 1/8 x, minus, yeah, antiderivative of cosine is a positive sign, and it was already negative. What are we looking at there? 1 over 12 times 8 sine 12x plus c. So what is 12 times 8? 96. Yeah, this is what I've been referring to as baby chain rule. You could use chain rule by defining u as equal to 12x, but the little guess and check, mini guess and check, is probably the way to go, because we already know that the antiderivative of cosine is going to be sine. You know the 12x is going to be part of it, so you can just kind of suppose, all right, well, if the antiderivative of cosine 12x has to be sine 12x in some capacity, then just off on the side or in your head, ideally in your head, but it's early in the process, you would say, what is the derivative of sine of 12x? Right, that would be cosine of 12x times 12. But we don't have a 12 there, so we correct for that. We would need to divide by the 12 in order for it to be the correct antiderivative. Okay? So if I know that through the antiderivative process I'm going to have to divide by a 12, that kind of leads you to a process that becomes something that you can generalize, and that is, if the inner function is linear, all you have to do is divide by the coefficient, right? And really that coefficient represents the slope. So just think in terms of logs, exponential functions, trig functions, any function of another function. When you're taking the antiderivative, you're going to rewrite it and make sure you divide by whatever the slope is of the inner function, right? In this case, it'll be constant, so that's not bad. You're welcome to include u substitution as part of your work, but again, time is an element of these assessments, so you want to get to a point where not only are you getting stuff right, but you're doing it efficiently.
In the first purple set you have there, couldn't you also pull out the 1/4 and then say 1/4 times sine squared of 6x times dx, or would that end up giving you more work?
I think it would be equivalent work, because once you get the sine squared of 6x, you then still have to do a substitution. Yeah. In the end, I think it amounts to the same thing, but you're not wrong to do it that way. You're just as right to do it that way. Right? So it's still a good strategy. And you're recognizing an identity, so that can never be a bad thing, So, all right, so I'm going to assign you number 4 for homework, but that goes on the back burner, obviously, because, did it come out yet? It just did? Okay. I exercised my teacherly right of doing the straightforward one in class and leaving the less straightforward one for you to do for homework. But once you realize that cosine to the cosine to the fourth is actually just cosine squared squared, then you automatically have your step one accounted for, because cosine squared is the same as 1/2 plus 1/2 cosine 2x, which is the simplified form. Well, maybe not, maybe simplified is not the right word, but the alternate form of the 1 plus cosine 2x all over 2. It's more convenient this way, because if I needed to anti-differentiate this, it's going to be easier to work with than the previous one. We do have to square this though, and it's a binomial squared, so double distributing FOIL, however you learned it. So 1/4 plus the outer terms, if you wrote it as two binomials, each of the outers and inners would each be 1/4 cosine 2x. Put them together, you get 1/2 cosine 2x. Plus 1/4 cosine squared of 2x. Now, it's up to you, but at this point, you can go one of two ways. You could do the substitution for the cosine squared, or you could integrate the things that are anti-differentiable. Well, I guess it's all anti-differentiable, but ready to integrate. You can take care of the 1/4 and the 1/2 cosine 2x, get those out of the way, and then do your substitution. You know, it varies depending on preference. Right? What I'm going to do is get all the substitution out of the way so I don't have to worry about it. One less thing to forget. This would be 1/4 times, so it was cosine squared of 2x, so that's going to be 1/2 plus 1/2 cosine 4x. Close them up, dx. All right, so you got to clean it up a little bit, a little distributive property, some like terms that can be combined. Well, really just two like terms that can be combined. Everything else is unlike, or not like. I don't know what the right way to say it is. Dislike. So 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x dx. So we're looking at 3x over 8 plus 1/4 sine of 2x plus 1/32 sine of 4x plus c.
Just the 1/8 cosine 4x dx to the 1/32 sine 4x. Can you explain how you did that?
So I anti-differentiated the cosine to make it sine, but then I had to divide by whatever the coefficient of x was.
Okay.
All right, so definitely intricate process there, but really, I mean, it's all substitution and simplification. From here to here is your calculus. There's really no other way to put it. It's just to say that in a lot of cases, the hard part about this stuff is the pre-calc. Right? And this is a topic that, you know, when you're dealing with double angle identities in trig, you didn't really do too much with it, because I can't even think of how you would phrase the question, or how one would phrase the question to get at this expression, the 3x plus 1/2 cosine 2x blah blah blah, from cosine to the fourth. The only thing I can think of is use double angle rules to rewrite cosine to the fourth of x in terms of first degree trig functions. I don't even know, like in pre-calc, I mean, you're just learning about what the word degree means. So if I gave you that verbiage, I mean, it'd be like, I don't even know what the hell you're asking, dude. So, you know, it's not as meaningful. So what I'm getting at is, if you didn't explore double angle identities in pre-calc, other than to say, all right, memorize these rules and maybe do an identity verification once or twice with them, that's not atypical. Yeah.
For the list of equations that we have to know, do we have to know how to do the ones with the H in it, with the hyper or something?
No.
A couple with equations.
No, that's optional subject matter, so I'm not going to assess you on it. So anything, yeah, the sinh, cosh, and tanh,
Yeah.
all that stuff, yeah, you don't have to worry about that.
Just made it like so much easier.
Oh, that's awesome. I mean, we're going to learn about that stuff, but I won't. It's not going to be on the AP, so I'm not going to force you to memorize those. Yeah, no, I'm not going to force you to memorize those. There was like 1% of me that was like, yeah, but what harm will it do? Eventually you'll have to know it, so why not? But that 1% just kind of went flying out the window. So anyway, look at these babies. Crazy. This goes under the category of rules that, like, I never would have come up with these on my own. But when I saw someone create them, you know, I saw them in a text, oh, these are nifty. And they come directly from your sum and difference identities for sine and cosine. So for example, the sine sum identity, sine of a plus b. That's sine a cosine b plus cosine a sine b. That you covered in pre-calc, definitely. The difference identity is the same thing, just with subtraction. Now, in pre-calc, you definitely spend some time expanding out a sum. So I'll just give you a quick example, just off on the side. I'll even pause the video. And we actually covered that. You know, you talk about linear approximations, differentials, and things like that. We can come up with something that could be a good estimator of what the true value is, but to come up with an exact value without the use of technology would be a different story. Right, so that's an application of it. I personally like going the other way. I think it's kind of cool, because if you have a product of trig functions, sometimes it could be collapsed down to just a single trig function of a sum or difference. Right, that's what these rules are trying to get at. Right, so if I look at, for example, the first identity here, sine A cosine B. Right, so you look at that and you say, okay, well, maybe I can find some value out of this. But to realize that all I'd be doing here is adding these two together and dividing by 2, so finding the average of these two identities, I never would have thought to do that. So I'm going to take the sum of these two identities. Let's move that over a smidge. All right, so the cosine A, sine B parts, they cancel out, and I'm just left with 2 times the sine of A cosine B. If I divide both sides by 2, I get the identity that I'm looking for. I don't know if I ever explicitly stated this, but because when I go through these little derivations, sometimes it looks like maybe math for the sake of math, fun fact of the day, he's showing off, that kind of stuff. It's really none of that. It's more so, I don't know that even I would remember these rules. But I had to remember these rules in pre-calc. And I remember them. So out of all of this stuff, just going back even to the rules on the top of the page, I don't remember those. I remember my double angle identities, my sum and difference identities, all the pre-calc stuff. So the tangent squared, secant squared rule, honestly, I never remember them. So I always pretend like I do. I know that tangent squared is equal to secant squared plus 1 or minus 1. I don't know. But I'm not sure about that, but what I do know is that sine squared plus cosine squared is equal to 1. And what I do is I divide very quickly in my head, I divide that by cosine, and so I get tangent squared plus 1 equals secant squared, bless you. So I'm not remembering the rule whenever I do it in class. I'm quickly figuring out the rule, all right? Now, would it be helpful if I could commit it to memory? Yeah, probably. But I think those days are gone for me. I can't even remember what I had for dinner last night, so, I mean, that's an exaggeration. I had a corned beef sandwich, appetizer sampler to start, 2 orders of the mozzarella stick. You pick 4. So we doubled up on the mozz, and we went with the coconut shrimp and buffalo wings, right? And then after that, and I thought the sauce was a little too peppery. They went with like a cacciatore type of marinara sauce. I didn't really appreciate that. So what we did was we saved most of the mozzarella sticks, and we brought it home, and then I just warmed up some Rayo sauce. It's a smart way to go. That's the intelligent approach. Then corned beef sandwich, with a little sauerkraut, melted Swiss cheese, and some dipping mustard. It's the traditional Irish approach to things. So yeah, so I remember food. I don't remember everything, but I remember food. But yeah, so okay, I don't remember this, but I remember that. And I can figure this out from that, all right? So that's where I'm at with this stuff. Now, maybe you're good at memorizing stuff, all right? Everybody has different strengths and weaknesses. I'll tell you right now that when I announced that we were going to be taking a quiz, or taking a set of quizzes just on formulas, I don't even have to take a poll. I know this just from experience. There's half the class that's like, yes, all I have to do is memorize stuff. The other half of the class is like, damn it, I have to memorize stuff. So it's a split. I mean, it always boils down that way. So we all have different strengths and weaknesses. Right? So some people are going to fall into the camp of, all right, yeah, I'll just make flashcards and memorize these, no big deal. And other folks are going to be like, well, this is going to be a struggle. how can I kind of cut corners on this? And this may be a corner that you cut. Now the problem is, if you don't know these rules to begin with, then you got nothing. You know, when I was mentioning before how I relate the tangent squared, secant squared right back to the sine squared plus cosine squared equals 1. If you don't know that basic Pythagorean identity, it's all over, right? So you have to know something, right? But if you have something as a basis, you can start there, right? So that's the sine, one of the sine rule derivations. I'm just going to write down for you the sum and difference identities for cosine, just so you have it. Cosine A plus or minus B is equal to cosine A, cosine B, minus plus sine A, sine B. And that notation, all it's telling us is that the minus goes with the plus goes with the minus. All right, so differing signs. All right. And in a similar fashion, you can add rules together in order to create new rules, you know, find the average and go from there. All right. Yeah. So if you have the rules available to you, like you would maybe in Algebra 2, did you get formula sheets in pre-calc? I hope not. Okay, good. So Algebra 2, though, you probably did.
Not on test, we just have to
Only
memorize.
on the final.
Yeah.
Only on the final? All right. Well, okay, at some point you did. Right. These are the kind of things that would probably appear on a formula sheet in one of those classes. As you know, formula sheets? What formula sheets? You know, so, you know, you ain't getting one of those here, so.
Yeah, everyone had that index card. I didn't know.
Oh, yeah,
I
the
didn't
gram.
know what the index card was for, so I did not have that. I didn't use
Oh.
Three.
That's a big oof.
Well, it didn't help anything.
Yeah, no, I actually used mine like maybe once a year.
That's why they gave those out.
Mm.
Yeah, right. You get the trick is
I
just
wrote
to-
all the major
All I had was
I-
the
It was so hard.
I let my students in the college bring an index card to each test, and there's always one person. First off, I gotta bring a ruler and a pair of scissors because I tell them it's a 3" by 5" index card, and there's always somebody who brings in like a piece of 8.5 by 11, and I'm like, yeah, that's not 3" by 5. They're like, wait, what?
Which corner do you
Yeah.
Where do you cut it?
I was like, well, I'll try to find you 15 square inches of area, roughly, of like actual notes. So I gave somebody a star-shaped one, like it's like crazy. One person gave me the spiel. They're like, listen, can you let it go this time? Because I only wrote on one side and I wrote really big. So like if I were to shrink it down, it would be like the equivalent. And I'm like, no, because nobody else knew that would be a thing. So I can't let you do it. And then not everybody else have that option. And then of course there's the other person who comes in with 15 different 3" by 5" index cards, all filled with notes, saying, oh, I thought we could have as many as we wanted. Be like, well, then why wouldn't I just let you bring your notebook? Like, if it was unlimited, why couldn't you just bring whatever? Then there was another person who tried that same stunt. She hid the other 14 under her purse so that she could swap them out as needed. The only problem is, I saw it because it's kind of like if you have, well, I don't have a purse, but imagine these things are the index cards, and this is the purse. It's like, okay, your purse is sitting on top of something that looks suspiciously like 3" by 5" index cards. So I mean, it's just it's insane what people try to get away with. So that, like I develop like a tick every time I think of index cards because that's like every time it happens I got to deal with this nonsense. Yeah, it's fun though. It's not fun.
Showed up, I was like, listen, I forgot the index card, but I can go get one from the Chicos. And
bring it back.
Chicos.
Chicos.
Yeah, we'll still leave the test 45 minutes
too
too
late.
late.
Yeah.
I feel like it didn't really help that much anyways, though. Like,
Yeah, I think I
help
used
at
it
all.
like
No,
one time.
everyone said that, so I didn't feel bad about it.
I kind of chuckle over the index card thing because, you know, what happens generally, I mean, very rarely do people use it to their fullest advantage, but generally what happens is people write down the stuff that they know on the index card.
Yeah.
Like, oh, let me write down this formula and that formula and that formula.
So true.
But they already know the formula. So the things that don't make it to the index card are the things that they don't know. Well, what I've recommended that folks do is like create a list of the things that you struggle with, you know, like just the topics, and then go through the notes and see if there's a formula associated with those topics, and at first try to learn it, then after that put it down on your index card. What that translated to, unfortunately, is just people copying other people's index cards. You're relying on other people having written it down correctly to begin with, so that's an issue. One person who was funny, in the middle of a test said, "Oh yeah, so I forgot to write this formula down on my index card, so I'm just gonna grab hers real quick, and yeah, I'm just gonna do that." And I'm like, "Well, if you do that, it's gonna be a 0. Like you're cheating." And I guess she thought I was kidding, so she did it, and I had to give her a 0.
Oh my god.
And as I'm saying, okay, so I just gave you a 0, she's like laughing. Like, oh, you card. You're like, I can't. You silly guy, you. And then as she's leaving, I'm like, no, seriously, 0 test. You're failing the course now. And she's like rolling with laughter walking down the hall. So I had to send her a follow-up email later on being like, just to clarify, you are now currently failing the course. To which she replied, LOL. I think it was only when I put a 0 on Blackboard, which is the grading system, that she was like, "Oh, you were serious." I'm like, "Yeah, like you can't just exchange materials."
That joke for so.
I mean, I have been known to hold a straight face for a fair amount of time, but yeah, it's like I don't understand what just happened. So. Oh yeah, she's like, this guy's hilarious. I'm like, oh.
Send a follow-up email just for the joke. I mean, that is dedication.
That's beyond extra.
Mr. Kenwood.
Yeah, actually, that is like definitely my MO. Yeah, so in example 5, we're looking at a product of sine and cosine. You know, so it follows the model of the first equation. So the A value would be 5x with the B value being 4x. So I'll just make a little note. That is not B, that's A. So we're looking at 1/2 times the sine of x plus the sine of 9x dx. Now, just like the formulas above, you have the concise way of writing it. I think we have it written here. But then you have the better way of writing it, which would be to distribute the 1/2. Because if you do it that way, then you could take advantage of the sum rule for derivatives and antiderivatives. And like everything else, limits, summations, everything. Which means we could take the derivative a part of the time. So we're looking at negative 1/2 cosine x minus 1/18 cosine 9x plus c. All right, so we're anti-differentiating the sine to make it negative cosine, but then dividing by the coefficient of x. In the case of the sine x, there's nothing to divide by, nothing other than 1. All right, so we're taking something where, I don't want to say impossible, but not overly practical, you know, in the original form, and writing it in a form that makes it a little bit more obvious how to find the antiderivative. Right? In this case, it looks like you could do it with some simple u substitution. you know, just define u is equal to the sine of x, and that'll, well, actually, no, you can't even do it that way. No, you still have to apply an identity because you don't have the same argument. If they were both, like, for example, 4x, then you could use u sub, but that's not the case here, right? But you can write sine of x as the sine of 5x as the sum of x and 4x, and then maybe simplify it from there, and then go u sub. But that just seems like a lot of work for something that, with a simple identity substitution, takes 2 steps, 2 unique steps anyway.